In this video, we will use some of the relations we derived in the previous section to calculate the speed of some common molecules. Let's look at hydrogen. Hydrogen is the most abundant element in the universe and is a rather common element here in the Earth's crust, yet there is very little hydrogen gas in the Earth's atmosphere. In this example, we see why kinetic theory can help us explain why there is little hydrogen in the atmosphere. To do that, we are going to calculate the root mean squared RMS velocity of some hydrogen atoms that are whizzing around in the upper atmosphere, the exosphere. Just a quick word here about the use of velocity and speed. We're not concerned with the direction of the molecules, i.e. in the true sense of velocity, as we know they are all travelling in random directions, so we often just refer to them as speed. The temperature of the molecules in the upper atmosphere is 2000 K. This seems hot for the upper atmosphere, so let's think about our understanding of temperature and also consider what we know about the upper atmosphere. So, although there are not a large number of particles in the upper atmosphere, this is sometimes called thin, the molecules that are there are moving very fast, and hence we have our high temperature. So let's recall our equation for the average kinetic energy. So the average of the square of the velocity equals 3 kT on m, but before we go any further, let's consider the mass of hydrogen. The mass of hydrogen is 1 atomic weight, and 1 atomic mass unit equals 1.67 by 10 to the negative 27 kilograms. Now actually we have a hydrogen molecule, which is H2, so we have 2 times 1.67 by 10 to the 27 kilograms. Now if we put in these numbers, we can see that the speed, and this should say RMS, is 4.97 kilometers per second at 2000 K. So if the RMS value of hydrogen at 2000 Kelvin is 4.97, we can compare this with the speed required to escape the Earth's gravitational field of 11.2 kilometers per second. We are still not able to answer this question. Let's do the same calculation for oxygen, as we know we have plenty of oxygen here on Earth. Let's write down the equation. And now the mass. The atomic weight of oxygen is 16, and again we have an oxygen molecule, O2, so we have 16 times 2 times 1.67 10 to the 27 kilograms. Now, if we add in the numbers and calculating this out, we see we get an RMS speed of 1.24 kilometers per second. So it's a fair bit slower than hydrogen. To understand why we have oxygen here on Earth and not hydrogen, we need to look at the final concept for this lecture, and that is the distribution of particles, or the probability versus speed, which is called the Maxwell-Boltzmann distribution. We have calculated the root mean squared velocity, but in fact there is a distribution of speeds, and not all the particles are travelling at this one speed. Some of the particles will be travelling much faster, and some will be travelling much slower. The probability of speeds is given by a function originally derived by James Clerk Maxwell and Ludwig Boltzmann, approximately around the same time in the 19th century, a time when the very existence of atoms was not even well accepted. Quite amazing, really. So let's plot two distributions to illustrate the concepts. We are plotting the speed versus the number of molecules. A blue curve with a higher speed and a red curve with lower speeds but a higher peak. So the mass 1 in this curve is higher than the mass 2. We could say that the mass 1 is represented by oxygen and mass 2 is hydrogen. Here is where the RMS speed is located on the curve. It's a slightly higher speed than the peak distribution, but the point to notice here is that there are still lots of molecules at even higher speeds still. Also, as the speed of the particles is proportional to the temperature, the higher the temperature, the faster the particles move. So in this case, the blue curve is the higher temperature and the red curve is the lower temperature. The key points of the Maxwell-Boltzmann distribution is that the distribution of speeds depends on both the mass of the molecule and the temperature. As the temperature of the system increases, the distribution is broadened and shifted. To understand why the curve has this shape, we can compare these blue and green curves. If we start with the green curve at the lower temperature, the area here represents the total number of particles. If we shift to the higher temperature blue curve, we need to have the same amount of particles, we're just increasing the temperature of our system, and hence we get a flatter but broader distribution. So thinking back to our escape velocity and our calculated root mean squared values for hydrogen and oxygen, we can see here that the escape velocity is only twice the root mean squared value for hydrogen. So a significant fraction of the hydrogen molecules are therefore able to escape at any moment, and hydrogen is therefore rapidly defeated in the atmosphere. How about the oxygen? The escape velocity is 8 times the root mean squared velocity for oxygen. As the kinetic energy is proportional to v squared, this means that in order to escape, the particles need to have at least 64 times the mean kinetic energy. It turns out from the Maxwell-Boltzmann distribution of particle speeds that only a tiny fraction of the oxygen molecules will have enough energy to escape, so most of them hang around here on Earth. What does this mean in terms of evaporation? If you think about water in a puddle at a particular temperature, room temperature, we now can understand that there is a distribution of speeds and that some of those particles will have enough energy to escape. And if we let the system sit for long enough, eventually all the particles will escape.